Hi everyone, it's Ms. Lopez. In this video we are going to talk about an FRQ practice where you're calculating solute potential. Let's get started. A student filled several dialysis bags, which are small plastic bags that are permeable to water, with a sucrose solution of unknown concentration. The student then placed the bags into beakers with 0, 0.2, 0.4, 0.6, 0.8, and 1 molar sucrose solutions at 29 degrees Celsius. The results are shown below. Part A asks you, what is the concentration of the sucrose solution in the dialysis bag? The sucrose concentration is going to be isotonic to the surrounding solution. So when you are looking at the solution of the bags, what you want to do is you want to find a solution where there is no gain or loss of weight due to the movement of water in or out of the bag. More specifically, due to the net movement of water. So what we're going to do is we are going to find our percent change in mass at 0 and find where that line crosses the axis, which is at this point right here. Anything above this positive change in mass means that the bag gained weight. Anything below this means that the bag lost mass, lost water, and so it had a negative change in weight. So we're looking for that isotonic concentration, which would be at a 0% change, which is at this point right here on this graph. Judging by the scale in this graph, to make this easier, I'm going to mark the halfway point, because the halfway point would be 0.7. So there is the halfway point. It looks like the line does not cross that halfway point. So it's just shy of 0.7. From here, I'm just going to have to estimate. This value here, halfway between 0.6 and 0.7, would be 0.65. So I'm looking at estimating a value between 0.65 and 0.7. About halfway in between would be about 0.67 or 0.68. This right here is the isotonic concentration, and we need that to be able to calculate the water potential of the bag, which is part B. So here's the formula for water potential. Water potential is equal to the solute potential plus the pressure potential. But since this is going on in a bag in an open system, the pressure potential is essentially 0, which means we can remove it from our equation. So the water potential is the solute potential. And to calculate solute potential, we need this formula. Now at this point, all we have to do is plug in our values. Most of these values are constants. The only thing we are going to need is C, the molar concentration, which we found in part A. So now let's plug in our values, remembering that the temperature needs to be in Kelvin. So I've plugged in my values. I is the ionization constant, and since this is in a sucrose solution, the ionization constant is 1. Remember that they will always give you the ionization constant. This is not something you have to memorize. C represents the molar concentration, which we found out in the first part was 0.68, so I plugged it in here. R is also a constant. This is known as your pressure constant, and that is in your formula sheet, so you don't have to memorize it. Its value is 0.0831 liter bars per mole K. But I wouldn't worry about putting any of the units in here because we're just going to type these into the calculator and get a value. T stands for temperature, and it must be in Kelvin. So I take the degrees in Celsius and add 273 to get to the Kelvin. So when I plug these values into my calculator, I get the solute potential of negative 17.1. Remember that there is a negative sign in this equation, so when you plug your values into your calculator, you will have to remember to make it negative. Solute potential is negative 17.1. Thanks so much for watching this video, guys. I hope it was helpful. See y'all later. Bye.